Assalamualaikum warahmatullahi wabarakatuh. My name is Amir Aiman bin Waizat. My number metric is CD240051. Today I want to present about an introduction. Thermodynamic is an essential branch of science that focuses on how energy transforms and interacts with matter, playing a key role in various engineering applications such as power generation, refrigeration, and HVAC systems. One of the most important components in this system is the steady state flow device, or SSFD, which allow continuous flow of mass and energy without any accumulation. Devices like compressor, turbines, pumps, and heat exchange are common examples. In HVAC system specifically, the heat exchange functions as a SSFD by transferring heat between air and refrigerant without mixing, ensuring effective indoor thermal comfort. Studying the performance of this device under real conditions is crucial for optimizing system efficiency, saving energy, and supporting environmental sustainable engineering solution. Thermodynamic is the study of how energy transforms and interact with matter, and it plays a key role in systems like power generation and HVAC. One important component is the steady state flow device (SSFD), which allows continuous flow of rates and energy without accumulation. In HVAC systems, the heat exchange is a key SSFD that transfers heat between air and refrigerant to maintain indoor comforts. Its performance depends on factors like temperature, pressure, enthalpy, and mass flow rate, making thermodynamic analysis essential for system efficiency. Studying steady state flow device (SSFD) is crucial in thermodynamics because this device controls the flow rate of energy and mass in many engineering systems. In industries, SSFD help optimize performance while reducing energy use. In HVAC system, heat exchange, one type of SSFD, play a big role in improving energy efficiency and lowering both operating costs and emissions. Understanding how SSFD works allows an engineer to predict system behavior, solve performance issues, and design generate more efficient system. It's not just theory, it's build real world problem solving skill for future engineering. The main objective of this study are firstly to understand and apply key thermodynamic concepts and how they relate to the operations of steady state flow device, or SSFD. We also aim to explore how important parameters like mass flow rate, enthalpy change, temperature differential, and heat transfer rate influence the performance of a heat exchange. Next, we will assess the efficiency of the heat exchange in maintaining a comfortable indoor climate within an air conditioning system. Finally, this study helps us identify ways to optimize performance, save energy, and improve system design through thermodynamics analysis.
So, Bismillahirrahmanirrahim. Assalamualaikum. My name is Afi Irfan bin Jamhuri, and today I would like to explain about the background and theory of SSFD. Alright, so when we refer to a steady state flow device, or SSFD, we are talking about a system where mass and energy flow continuously and uniformly through the controlled volume over time. In other words, the system's condition remains stable during operation. In HVAC system, classic example of SSFDs are heat exchangers like evaporators and condensers. These components operate under relatively steady condition within each refrigeration or cooling cycle, making them ideal representation of steady state flow behavior. Alright, so next, I will explain about the thermodynamics laws and principles. Right, so the first law of thermodynamics for open system relates heat and work transfer to changes in enthalpy, velocity, and elevation. It's expressed as Q dot minus W dot equals M dot times the change in enthalpy, kinetic energy, and potential energy. However, in most heat exchangers, changes in velocity and elevation are negligible. So, the equation simplifies to Q dot equals to M dot times H2 minus H1, meaning heat transfer is directly related to the change in enthalpy. So, the second law complements this by ensuring that the heat always flow from a higher to a lower temperature. It also helps define how efficient the process is, especially in a system like heat exchangers where minimizing energy loss is critical. Hi. Alright, so for the next slide, in an air conditioning system, the heat exchanger plays a key role in regulating temperature. First, warm indoor air passes over the cold evaporator coils where heat is absorbed by the refrigerant. Then, this high temperature refrigerant is sent to the condenser coils where it releases heat to the outside. The effectiveness of this process relies on three main factors: the temperature difference between surfaces, the thermal conductivity of the materials, the surface area of the coils. Maximizing these factors ensures higher efficiency in heat transfer. Alright, so last but not least, there are several benefits to use steady state flow system in HVAC applications. Alright, so first, they offer enhanced energy efficiency, reducing power consumption. Second, they ensure consistent cooling performance, which is crucial for comfort and reliability. And third, they allow for easy system modeling and diagnostics, making design and troubleshooting more straightforward. However, there are also challenges. Alright. First, maintaining a true steady state during real-world operation can be difficult due to load changes. Second one, scaling the system to handle variable loads and environmental conditions require careful design. And finally, issues like refrigerant leakage or flow instability must be managed to preserve system performance. Thank you.
Assalamualaikum, my name is Khairunaz Arman Afandi bin Khairun, manometric 240292. The real world system we're examining is a vapor compression air conditioning system, mainly used in homes, office and vehicles. One of the most critical components in this system is the condenser, which functions as a steady state flow device, or SSFD. This means it operates under constant flow conditions, where mass and energy enter and leave the system continually. In this case study, we focus on analyzing the condenser thermodynamic behavior. We want to see how its performance is affected by change in key parameters like inlet temperature and mass flow rate. Understanding this effect help improve energy efficiency, system reliability, and overall cooling performance. The condenser receives high pressure refrigerant vapor from the compressor and release heat to the surrounding air. In this case, we use R134 as the refrigerant entering the condenser at 80 degrees, with a mass flow rate of 0.05 kg per second. Using the first law of thermodynamic for steady flow system, we calculate the heat reject as Q dot equal M dot multiply H in minus H out. M dot 0.05, H in 276.9, H out 95.5. The answer is 9.70 kilowatt. This shows how the condenser maintains thermal balance in the system by rejecting this much energy. Because the flow and energy transfer are constant over time, it perfectly matches the definition of an SSFD. There is not accumulation of mass or energy inside the condenser, only a continuous transformation from vapor to liquid. Next, let's look at how changing operating condition affects condenser performance. If we increase the inlet temperature from 80 to 90 degree, the enthalpy increase, and so does the required heat removal. The new heat ejection rate become approximately 9.73 kilowatts. This creates a heavier load on the condenser, which may lead to reduced efficiency or overheating if the airflow or surface area is sufficient. Now, if we increase the mass flow rate to 0.07 kg per second, the heat rejection risks to 12.7 kilowatt. This result is faster cooling, which can be beneficial, but it also increases energy consumption and may require bigger components or better airflow. In both cases, we see that small change in system parameters can significantly affect performance. So, precise control and understanding of these parameters are crucial to achieving stable, efficient cooling.
Assalamualaikum warahmatullahi wabarakatuh. My name is Amirul Iman bin Muhammad Zahar and my matrix number is CD240126. So, let's start with a quick summary of the condenser's performance. Under normal conditions, the condenser removes 9.07 kilowatts of heat. When the inlet temperature increases to 90 degree, heat removal goes up to 9.73 kilowatts, which may strain the system if it is not properly designed. If we increase the mass flow rate to 0.07 kilograms per second, heat rejection rises to 12.7 kilowatts. That sounds good, but it requires a larger condenser or more airflow to be effective. Now, let's talk about the strength of using the condenser as a steady-state flow device. It performs predictably under steady flow and has no moving parts, making it reliable and low maintenance. Most importantly, it plays a critical role in keeping the air conditioning cycle running smoothly. However, there are few weaknesses. The system is sensitive to change in flow rate and environmental conditions like outdoor air temperature. Over time, issues like leaf falling or clogging inside the heat exchanger can reduce efficiency. And if the flow or heat load is not well controlled, the performance drops significantly. From this case study, we learn some important lessons. First, a solid understanding of thermodynamic is essential for designing systems like this. Second, performance really depends on optimizing flow and temperature control. If those are not managed, efficiency drops fast. And finally, the condenser directly impacts energy usage and user comfort, even though it doesn't have any moving part. To improve the system, we suggest adding automated controls to adjust refrigerant flow and airflow based on demand in real time. We can also switch to better heat exchanger design, like micro-channel condenser, which transfer heat more efficiently. It's also smart to use eco-friendly refrigerants that have better thermal performance and lower environmental impact. Lastly, regular monitoring and designing the system to handle seasonal change can keep it running efficiently all year round.
Assalamualaikum and good morning. My name is Ahmad Faizi bin Jamsari. My matric number CD240115. To conclude this study, analyze a heat exchanger as a steady-state flow device or SSFD. Using the first law of thermodynamics, we focus on energy conservation, mass flow rate, and thermal efficiency in heat transfer. The key findings show the heat exchanger performance mainly depend on factors like mass flow, temperature difference, and enthalpy. Tuning this improve energy saving and system reliability. However, issues like falling and environmental change can reduce performance. The study also highlighted the need for steady state assumption while also acknowledging the benefit of future improve like advanced control system and no refrigerant. Overall, this research show the importance of SSFD in designing efficient and sustainable HVAC system.